Hello everyone, my name is Alok Parmar and I am MS by Research student at International Institute of Information Technology, Bangalore. Today, I am here to present our work FastMem, a fast architecture-aware memory layout design. The co-authors of the work proposed are Kailash Prasad, Nandita Rao, and Joyce Miki. The work is in collaboration with Indian Institute of Technology, Gandhinagar, and it is accepted for publication in 23rd International Symposium on Quality Electronic Design, I Squared 2022. This is the outline of my presentation. Next, we move to motivation of our work. The goal is to develop a tool for accurate and fast SRAM modeling for architecture level study with ASIC layout. Memory designs can be extremely challenging and time-consuming task, which includes several exploratory studies to find the most optimal size of the array. Thus, to speed up the memory design, it is imperative that the low-level circuit details should be masked when doing an architecture analysis. Hence, the current challenges are considering the complexity of the memory array, large exploratory studies are required to find the optimal memory configuration. Existing simulators like CACTI models SRAM, but the accuracy is less for the fabricable technology. Other studies are based on low-level circuit details or SPICE simulations, which are extremely slow. Optimal memory configuration and ASIC layout is required. Hence, the proposed approach is FastMem that allows designers to obtain memories with the highest area efficiency and least energy relay product using an architectural tool, which can then be fed to a memory compiler to obtain the final layout. SRAM architecture in CACTI simulator. The figure shows the architecture of memory array in CACTI. As we can see, at the highest level, the array is composed of multiple identical banks. Hence, each bank can be concurrently accessed and has its own address and data bus. Next, each bank is composed of multiple identical subbanks with one subbank activated per access. Each subbank is composed of multiple identical mats, and all the mats in the subbank are activated during the access, with each mat holding a part of the access word in the bank. Also, each mat itself is a self-contained memory structure that composed of 4 identical subarrays and associated pre-decoding logic. Each subarray is a 2D matrix of memory cells and associated peripheral circuitry as shown in this figure. FastMem. FastMem is a framework that uses an open source tool, CACTI, with OpenRAM as shown in the figure. It takes inputs as the memory size and memory arrangement in terms of banks, subbanks, mats, peripherals, technology nodes, and it optimizes the design for a given parameter such as delay, energy, and so on. The subarray and the final memory layout is provided in the form of netlist and layout from the OpenRAM, accepting the optimized parameters obtained from the CACTI. Comparison between CACTI and OpenRAM. CACTI is an architectural simulator to calculate the memory access time, cycle time, area, leakage, and dynamic power model. OpenRAM, on the other hand, is a memory compiler that provides a platform for generation, characterization, and verification of memory designs across various technologies, sizes, and configuration. The table here shows a general comparison between both the tools. CACTI, being a high-level simulator, generates quickly the space exploration, design exploration results. However, since it is based upon the analytical models and not the detailed and layout simulations, the results generated by the CACTI is less accurate, whereas the OpenRAM supports generating ASIC layouts and it gives extremely accurate results. Both the tools support timing and power analysis, whereas the OpenRAM only supports assisting ASIC layout. The ease of technology scaling and ease of architecture level analysis is easy and in CACTI as compared to Open RAM. 65 nanometer technology modeling in Open RAM and CACTI. Open RAM currently supports free PDK 45 nanometer and SCMOS 300 nanometer technology node. We have modified Open RAM and ported it to 65 nanometer technology node. The tool can generate and characterize memories up to 4 KB. However, after parasitic extraction, the post-layout simulation using caliber takes around 30 hours for 64x64 memory array. So, for fast and accurate characterization of large memory arrays, we have extended CACTI to support 65 nanometer technology node also. The 65 nanometer technology parameters are extracted through the Cadence Virtuoso tool simulations. The extended CACTI takes few milliseconds to characterize the memory subsystem of size 64x64. Characterizing CACTI and Open RAM. To compare CACTI and Open RAM, we have modeled 60 SRAM subarrays ranging from 64 bits to 1 KB in both CACTI and Open RAM. We have compared the CACTI and Open RAM for maximum frequency of operations and dynamic energy. As we can see from the figure, although there is not a complete overlap between the results, there is a close match. Results from both the tools indicate that the propagation delay increases as we increase the size of the array, which results in decrease in the frequency of operation. Further, both the tools give the same trend in dynamic energy, where the dynamic energy per axis increases on increasing the number of rows or columns as shown in the figure. Hence, we have validated the maximum operating frequency and dynamic energy per axis obtained through CACTI and Open RAM for 65 nanometer bulk CMOS technology node. Results validation for large memory array sizes. Next, to compare the compatibility between both the tools for higher subarray sizes, the access time results of Open RAM are compared with CACTI for free PDK 45 nanometer. Larger sized memory arrays are divided into multiple banks to decrease the overall access time in both Open RAM and CACTI. The figure shows the access time trend for larger sized memory arrays. Here, what we can see that both the tools provide again a close match in the results, and therefore for the rest of our analysis we choose CACTI for the initial design space exploration, which can be carried out in very quick time. Figure of merit. To find the optimal memory array configuration, we introduce a metric called as figure of merit, which is defined as the area efficiency by EDP. The objective here is to find the configurations which leads to the best FOM values. Here, the area efficiency is defined as the total area occupied by the SRAM cells to the total memory area, including the peripherals. Optimal subarray configuration. Here, the normalized FOM plots are depicted. We demonstrate the impact on the performance on the single subarray for different configurations, which is rows and columns of the subarray. In each case, in our simulations, we accessed 64 bits inside the subarray and adjusted the degree of bitline multiplexing for each subarray configuration. We present the results for 7 nanometer FinFET, 32 nanometer and 65 nanometer bulk CMOS technology nodes. Here we can see that FOM is high for square or unskewed subarray arrangement for bulk CMOS technology, whereas for FinFET technology nodes, FOM is high for skewed subarray. Access time and dynamic energy plot across technology. To understand the previous behavior in detail, we compared the individual peripheral and memory cell delays for both bulk CMOS and FinFET technology nodes. We plot the breakdown of access time and dynamic energy per access for 32 KB subarray for 256 cross 1024 arrangement in a stacked pie plot as shown in the figure. The outer pie plot indicates that the breakdown for the access time and the inner pie plot indicates the breakdown for the dynamic energy. The output circuitry in the graphs refers to the sense amplifier and the output driver circuit. We observe that from the outer pie plot, the contribution of bitline delay reduces as the technology scales. On the other hand, the peripheral and interconnect delay in the 7 nanometer node contributes heavily to the access time. Hence, we can conclude that at lower technology nodes, for optimizing the overall performance of the memory array, more attention needs to be paid on optimizing the peripherals and interconnects rather than the actual SRAM cells. FOM for different bank size. Next, to optimize our memory array, we now study the impact of banks on the performance of the array using CACTI. As the size of the array is increased, access time and energy consumptions become a matter of concern. Large subarrays results into high access time, whereas the large wire capacitances results in the increased dynamic energy. A possible solution that we adopt is to partition the complete array into smaller units. The first hierarchy of segmentation, as discussed, is to divide the complete array into multiple banks. For our experiments, we assume that each bank consists of only a single subarray and 64 bits of data is accessed from the memory. We varied, as shown in the figure, we varied the size of the array from 32 KB to 128 KB for different number of banks. Further, we also consider the arrangement of number of rows and columns inside the subarray. We plot the graphs for FOM to determine the optimal number of banks in a particular array. We can see from the graphs that increasing the number of banks improves the FOM for larger sized memory arrays. However, increasing the number of banks beyond a certain optimal number decreases the memory array's FOM. Optimal bank configuration. After defining the optimal number of banks in a memory array, we obtain a complete arrangement of banks that results in maximum performance gain. We recognize that as the size of the on-chip memory increases, each bank inside the array is usually partitioned into multiple subbanks. Each subbank is divided into multiple mats, and each mat contains 4 subarrays, as we have discussed earlier. The array partitioning helps us to reduce the delays due to long bit lines and word lines as compared to the non-partitioned array arrangement. The table shows the optimal array configuration for 65 nanometer bulk CMOS and 7 nanometer FinFET technology. Here we can see that most of the optimal configurations of the banks are divided into subbanks and mats. In 65 nanometer bulk CMOS technology, FOM is highest for square or near to square layout. Again, non-square arrangement leads to the best FOM for 7 nanometer FinFET technology node. NT and ST analysis for 7 nanometer FinFET technology node. In this section, we extend our study on 7 nanometer FinFET technologies to study the behavior of the subarray at near threshold, which is NT, and standard operating voltages, ST. We further extend the study to 80 SRAM cell configuration for 7 nanometer FinFET technology. From the figure, we can see that the optimal point, FOM point for both 60 and ST is 80 is different for NT and ST operations. The optimal point for ST voltage is skewed. In contrast to the optimal point of NT operation is unskewed arrangement or the square arrangement for 7 nanometer FinFET technology node. Again, to understand the deviation of the optimal point for different supply voltages, we plot the breakdown of access time and dynamic energy per access for 32 KB subarray for a 512 cross 512 arrangement in a stacked pie plot as shown in the figure. Again, the outer pie plot indicates the breakdown of the access time, and the inner pie plot indicates the breakdown of the dynamic energy. For the ST operation, we observe that the contribution of peripherals to the dynamic energy and access time is nearly twice as compared to the NT operation. Therefore, for NT operation, optimal FOM points are obtained with square subarrays as opposed to skewed subarrays during ST operation. Optimal layout using OpenRAM. The last stage of FastMem is to generate the layout. After obtaining the optimal memory configuration from CACTI, we feed the design parameters to OpenRAM to generate the layout of the memory array. The figure here shows the layout for the optimal 256 cross 256 subarray for a 32 KB memory array, which is a single bank structure designed generated using the OpenRAM. Here, the SRAM subarray is depicted, and also at the left hand side, decoder wordline driver address D flip-flop. On the bottom, we have pre-charge, sense amplifier, write drivers, and data flip-flop. Also, we have a control circuitry at the bottom left corner. The dimensions of the layout is also provided. Key takeaways. The proposed FastMem performs a large design exploration to obtain an area-efficient memory designs with the least energy delay product. This methodology helps us to combine the speed advantage that the tool such as CACTI offers and the ability to generate layouts that a memory compiler such as OpenRAM offers. A square configuration of the subarrays resulted in the optimal performance of the bulk CMOS technology node, whereas a non-square arrangement for the 7 nanometer FinFET node is resulted in the best performance. The peripherals and interconnects in the 7 nanometer contribute nearly twice to the dynamic energy and access time as compared to 32 nanometer node. The optimal FOM point is different for near threshold and standard voltage operations. The optimal point for standard voltage is skewed. In contrast, the optimal point for near threshold operation is unskewed arrangement or the square arrangement for 7 nanometer FinFET technology node for both 60 and 80 SRAM cells. Author's information. In case of any doubts or suggestions, feel free to contact the given email addresses. Thank you.